Here, now we're more or less ready to go. So what's going on today? Today we're going to be looking at harmonic motion in a spring mass system. And I wanted to start by talking about what are the different possible sort of motion curves that we could have. And if we think about having the general spring mass system that looks like this, mx double prime plus cx prime plus kx is equal to some function of t, f of t, then it may be worth reminding ourselves what all these things are. We have m is the mass. We have c is the damping constant. We have that k is the spring, or what I like to think of as the restoring constant. But sometimes I think it's just called the spring constant. But what it's really doing is it is restoring the spring to its natural length. That's why I like that name. It's just a better reminder of what it's actually doing. And then finally, we have a driving force, which could be zero. Now, when we try to find solutions to this, whether there's a driving force or not, there will be a complementary solution. If the driving force is zero, then the complementary solution is the whole thing. If the driving force is not zero, then we want to find a particular solution as well, and then combine it with the complementary solution. But either way, there's going to be this initial part where you're finding the complementary solution. Usually the term complementary solution is only used in the context of a non-homogeneous linear differential equation. I'm going to use it for both cases just so that I don't have to differentiate between the two. So the complementary solution will depend on how m, how c, and how k relate. And in particular, if we back up a second and we find the characteristic polynomial, in general, that's going to be, I'll use r for my variable, p of r. That's going to be mr squared plus cr plus k. And if this is review for you, that's great. If it's not, or it's a little fuzzy, that's fine too. But either way, I just want to make sure we have this on our minds as we go forward, because it'll make it way, way easier. So once we have this characteristic polynomial, we then want to find the roots. The roots are going to be negative c over 2m plus or minus 1 over 2m, and then square root of c squared minus 4mk. And this c squared minus 4mk will tell us a lot about what the roots look like, or what the solution curve looks like as well. And then also whether c is 0 or not is meaningful. So there's a few things to keep in mind. If c is equal to 0, then the system is undamped. So that's one thing to look for. I mean, that makes sense, right? If the damping constant is c and it's 0, then there's no damping. And then after that, one looks at the discriminant to decide 3 other potential cases. Depending on whether that's greater than 0, equal to 0, or less than 0, will decide what kind of motion you have, at least from the complementary solution portion. Jumping to another page, if we have c squared minus 4mk is greater than 0, which inherently means that c has to be greater than 0. Why is that true? Because m and k are greater than 0. And c, well, c's either going to be 0 or non-zero, and it rules out the case that you'd have 0. Otherwise, this whole thing could not be greater than 0. If that's going to be the case, then what you have is the following. Supposing the vertical axis is x, the horizontal axis is t, and I'll move this over a bit. What you get in that case, and maybe I'll even color this to highlight, what you get in that case is something kind of like this. Then if you have, let's say, c squared minus 4mk is equal to 0, you'll have something that looks pretty similar. It'll look the same, except in comparison, it will approach the t-axis faster. It'll sort of drop quicker. So it might look something like this. Same basic shape, but it just drops faster. And then the final case, c squared minus 4mk is less than 0. That's where you have now some type of oscillation. And then there's, I don't know if I call it a subcase, but there's a version of that beyond. If c is equal to 0, you could have that this c squared minus 4mk is less than 0. That's certainly possible. If c is equal to 0, then what you have is, color should I use? I'll use green. You have the same type of thing as above, but now you don't have the oscillations or the amplitudes dampening. So you have something like that, where it maintains the amplitude throughout. So this would be where c is equal to 0. And once you have c is equal to 0, you need some mass that will be positive. You need some k that'll be positive. So c equal to 0 should be all you need if it is really representative of a spring mass system. All right, now these all had an implicit assumption that we weren't focused on the driving force. With the driving force, there are two other cases. So that we have it all on the same page, I'm going to create a box here. So all these outside of this box, they are all concerned with the undriven system. So in all of these, f of t is equal to 0. If you want, I can sort of copy that each place, copy and paste. All of these, f of t is equal to 0. If you have that f of t is not equal to 0, then there's going to be, and you can have different types of behavior. The two types of behavior we'll be concerned with are resonance and beats. Let me take the same set of axes. So with resonance and beats, we get those by looking at the complementary solution and the particular solution and comparing. And I'll just say in the first case, if, let's say, the complementary let me write it more simply. Let me just say no overlap. And what I mean by no overlap, instead of writing, I'll just explain it. What I mean by this is the complementary solution and the particular solution don't share similar terms. If that's the case, then what you'll have is beats. And let me put this in a different color yet. So to look kind of something like this. And how I'm meaning to draw this is kind of like so. Like there's these envelopes. I like to call them beat envelopes. Kind of like this, where there's a sort of overall oscillation, and then there are these little sub-oscillations, if you will. So this would be beats. Then in the other case, where there is overlap, and again, when I say overlap, I mean overlap between the complementary and the particular solution. Let me maybe note that for visual reference. If there is overlap, then what you get is this how do I want to say it? The driving force is in sync with the complementary solution, and it drives up the amplitude. So instead of dampening out, what you might get is something kind of like this, where your amplitudes get bigger and bigger. And of course, for engineering people, I'm sure you have heard of, things like the Tacoma Narrows Bridge and so on. where I think it was the wind blowing on it sort of resonated with the traffic going over it, and then it started, just oscillating wildly out of proportion to what was intended, and it just broke itself apart. So this is resonance. And maybe to give a name for each of these things, we have overdamped in this very first case up top. We have critically damped. We have underdamped, but still damped. But then when C is equal to 0, we have undamped. There's no damping. And finally, we've got beats. And we have resonance. And there are different types of resonance, but I'm not going to get that specific at the moment. Okay, with this in mind, and I'm recording this, so you can always come back and check out this sheet later. Why don't we go ahead and look at the applet? So I'm going to stop this share. And I'm going to share this applet here. All right, here we go. Now, what we want to do with these 6 graphs, and maybe let me say something about these graphs quick. Notice what we have, and let me get the annotation. I'll help highlight as I'm talking. What we have here is a spring mass system. You'll notice it's the mass times the second derivative, C times the first derivative, and then K times the 0th derivative. That's going to be equal to a driving force, which in this case, the only driving force we can have is some number times cosine at some frequency. So we don't have complete control over what driving force. It's just going to be something with cosine, but that's okay. But otherwise, this is just our spring mass system. And we have a second order differential equation. If we want to know an exact solution, we need 2 pieces of information because it's second order. And we've got 1 here and then 2 here. Now, as you change these numbers, for instance, if we change, if I change, let's say this to, say 4, and I update this graph, the graph that gets updated is the blue one. So the one that's displayed by the numbers we put in here is the blue. Like if I change this to, let's say -2 or whatever, I get this. Our goal is to try to match up the blue line. We want to try to pick the right values so that we get the blue line to match the red one. So we look at the red one and say, okay, what kind of motion is this? And let's try to pick values accordingly so that the blue line will match that. So we choose the system to match the motion type. Now, before that, it might be worth mentioning for each of these just simply what type of motion it is. So let's go through and look at number 1, 2 through 6, and we'll just decide what's the motion type. That'll help orient us. So I'm going to ask you and look to chat just to kind of see where we're at here. What do you think number 1 is with the following options? Overdamped, critically damped, underdamped, undamped, resonance, and beats. There's 6 options, the options we just looked at. So what do you think? And when I say something like overdamped or critically damped, when I say that, I'm also meaning unforced as well. Okay, good. I thank you, those who put responses in chat. I'm seeing a lot of good stuff. So it does end up being undamped. The reason it's being undamped is because, well, one, as far as the red, I should say, as far as the red, and maybe I wasn't clear about that. So looking at the red is undamped because the oscillations do not change. Or I'm sorry, that amplitudes do not change. It looks like the amplitude is always 4, and that never changes. And it does oscillate, so that's undamped. If we go down to the second one is also undamped. I want to ask because I think it'll probably be obvious if the first one was obvious. The amplitudes are now 3, and that's really about it. It has a higher frequency. It looks like the max is reached more often within, let's say a second or a given time interval. So it's faster with lower amplitude. How about 3? What do y'all think for 3? Looking at the red line. So what is the red line for 3? Is it overdamped, critically damped, undamped, underdamped, resonance, or beats? Okay, to those of you who responded, thank you, appreciate it. Yeah, and I see there's some question, critically damped or overdamped. And the answer to that is, well, it can be hard to tell between the two. It is one of the two. I'm not sure offhand which. I don't know how to visually check and see. But we know it's at least one of those two cases. It's certainly not underdamped, and it's certainly not undamped. And there's no resonance or beats. So critically damped or overdamped, it's certainly going to be one of these two. So we know roughly a range of the two. Okay, good. How about 4? What do y'all think for 4? And I'm going to type in chat just to differentiate that now we're talking about 4, just so I know when the answers change. Okay, yeah. Again, thank you for your responses. It seems pretty clear. We know that is underdamped. Excellent. That there's oscillation, but it's sort of dying out. It's not undamped because the amplitudes change. Okay, now 5. What do we think for 5? Okay, yeah. All right, y'all got it. You're just rocking this, just a nonstop stream. It is beats for 5. Nice. And then how about 6? You got 5, probably 6 is easy, but just for the practice. All right, looking good. Cool. Yep, 6 ends up being resonance. With that in mind, keeping an overview here, with 5 and 6, in order to get 5 and 6 beats or resonance, we need the driving force to be not 0. So that's going to be the case where we put something besides 0 for the cosine coefficient. The rest of these should have 0. So we won't mess with the cosine coefficient for 1, 2, 3, or 4. We will mess with the other things. And I want to point some things out. Notice in the first case, I think it was set up like this. Yeah, that looks about right. Now pay attention to the initial value information. The initial value is 1. So at time t equals 0, we start out at 1. And the initial velocity, x prime, at t equals 0, is 0. So that means, let me get the annotation. That means that we start here and there's a slope. Maybe I should do a different color. There's a slope of 0, and that comes from this thing right here. You can change both the starting position and the starting velocity. For example, I could change the starting position to 0, which is where we start. But notice, because the starting velocity is 0, that means we'll just get the straight line. It looks like the slope is positive, so what I might do is I might change this to 1. And now it's still not quite aligned, but it's something maybe a little better. And you can experiment. Maybe you can, increase the initial velocity and so on, and play around with it. You may be able to see where this is going, and I won't quite finish it off. I just want to give you the opportunity to, but I wanted to point these things out. So I'll let you experiment with number 1 a little bit more, but let's now talk about 2. In fact, there's not much left to do with 1. We're talking about 2. With 2, it's the same kind of thing with 1, where notice we have a starting position that's obviously it's not 1, it's higher. and it looks like the initial velocity might be 0 or it might be a little negative. You can kind of look at this spot and judge it for yourself. I'm not totally sure what I would call this. Could be 0. It could be like a tip like that. Why am I not getting it? There we go. It could be, something like so, or it could have like a little downward slant. You'll have to experiment with it, but otherwise I think it's somewhat similar. But there is a difference in the frequency. Whereas up here in the first case, I don't think you had to experiment with much beyond the initial velocity and position. In this case, I think we'll need more than the initial velocity and position. In particular, we'll need it to oscillate faster. And the question is, how do you do that? And if you are already experimenting with this while I'm talking, that's great. I'm just trying to give supplemental information. You don't have to wait on me to do any of this. But if it's helpful just to follow along and wait, that's fine too. So besides messing with the initial velocity and position, to get a higher frequency, we should maybe think about how you change the frequency. I'm going to get text here. So if we think about that discriminant, or we think about the roots. So what were the roots? The roots were r is equal to negative c divided by 2m plus minus. And when we did plus minus, we had square root. Actually, we had 1 divided by 2m. Then we had square root. And in that square root, we had c squared minus 4mk. Another way to write this is we had r is equal to, how do I want to put it? A plus, like if we just kind of relabel A plus or minus B. Do I want to say that? Yeah, let's say that. A plus or minus B. If, well, I can't quite say just B, because we could have I there. Let's just put an I there. Let's just assume that it was such that we ended up with an I. So we'll assume that c squared minus 4mk is less than 0. Okay. That way we get an I here. So in that case, what we ended up with was, let's say, C1 e to the a times t times cosine of b times t. And then we had plus C2, same thing with sine. EAT. And then we had sine of BT. So if you want to change the frequency, that has to do with B here. The A portion, the negative C over 2m, that will just determine the dampening. But there's no dampening here. It's undamped. But how fast it goes depends on B. And we can see that B, well, C is going to be 0. So it just depends on M and K. So you want to mess with M and K to get a different frequency. So I'll let you experiment with that. The next thing I want to point out, actually, I don't know that there's much more to point out here, 3 or 4 really. Maybe I'll say something about 5 and 6. So I'm going to clear, I don't want to put this. Okay, yeah, actually I'm going to keep the same information. So with 5 and 6, imagine you go through and you get this complementary solution, which should still be on screen. The C1 e to the AT cosine BT, etc. it should be that it's even better than that. I would start with, for beats and resonance, actually letting the damping be 0. So let's suppose we even let C be equal to 0. So the damping is 0. What that gives us is a complementary solution of C1 cosine BT plus C2 sine of BT. B is, whatever value. Now, if that's our complementary solution, in order to get, and let me highlight here, let's try magenta. In order to get beats, what we want to do is to look at these two sets of things. We want to look at the driving force, and then we want to look at the trig terms in the complementary solution. In particular, we want to look at the frequency. So we'll notice here, well, maybe I'll change the color. We have a frequency of 1, and here we have a frequency of B, or maybe I should say angular frequency. So we have this, don't quote me on this, I think it's actually angular frequency. But we have that these are different values. We want them, or we have that they potentially can be different values. That's what we want for beats. We want the two frequencies to be different so that they don't coordinate and sort of drive things, like amplify the amplitudes, like what would happen in resonance. If they're in sync, then they work together to just continually increase the amplitudes. But if they're out of sync, that's where you get this sort of interesting overall oscillation and then sort of sub-oscillation. So what you want in this case is to make sure that whatever you come up with for your B, based on this thing here, you have something different here. So you can try to first figure out a general form for the complementary solution on the left, and then from there, experiment with this value to try to get it just out of sync in the right way so that you get this behavior. And then in the second case, let's see, will this work? There we go. In the second case, what you want is for the values in the green boxes, you want for those to be the same. So you want to first, maybe on the left, kind of determine what you want that to look like. As far as maybe you want to pick the values so that you hit 0 always at the same spot. I mean, this does not, notice it kind of looks like the red curve is twice as fast or twice as frequent. So you'd want to choose it so the frequency seems the same, or rather that, yeah, no, I'm saying that right. Yeah, the frequency seems the same, and then also that your initial values will work out. And I think once you then have that, it should be in sync. But either way, if you look on the left and you come up with whatever the complementary solution should be, then you want the B values here that you get from that complementary solution to line up with what you have here. Okay, maybe I've over-explained that, but hopefully that makes some sense. And now I'm actually going to just let you continue to work, and I'm going to go silent. And as you have questions, let me know, and I'll be happy to help out. Okay, someone asked about looking at the instructions, how to submit answers. I am going to look at the instructions now and answer that question. So turn in, looks like everything but 8. Okay, so what should you turn in? So what you would want to do, for instance, when you actually turn your work in, is you'd want to say something like this. You want to say something like, for number 1, it is undamped. And then you might say that the initial value problem is x double prime plus x is equal to 0 with initial value information x of 0 is equal to 0. And then I'll just give you the answer for this one. I think it's x of 0 is equal to 4. And then for number 2, what you might do, we also decided that it's undamped. I don't actually know what it is, but you sort of write that initial value information like so. And let me go down here. Did I lie to you, or is it actually 4? It is actually 4. So if it wasn't clear what we're trying to do, notice what I did for the first one is it started out 1, 0 like this. I changed the initial value, x of 0, initial position to 0. Then I changed the initial velocity to 4. And now what we have is that the blue line overlaps the red one perfectly. Then that gives us an initial value problem, which is this right here. And that's what you'll want to put in your write-up along with the damping type. The damping type is undamped, as we decided. So hopefully that answers the question about how do we write it up. So you're really just going to do something like I've drawn here. Just say, number 1, it's undamped. Here's the initial value problem. 2, it's undamped, blah, 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 blah. There's the initial value problem. If that doesn't answer your question, let me know and I'll try to rephrase it. Okay, another question was, how exactly do the red and blue lines need to line up? And that I think I answered through, just like in this problem right here, where I've chosen the values in the initial value problem such that the blue line now overlaps the red one totally. So if you have it completely overlapping, then you've picked the right initial value problem. Another question is there a way to do it that's not guess and check? Yes. For example, with this first one, I didn't really do any guessing. If I go back, so I want to clear this. So if I go back to the very first problem, it started out like this. One thing I noted was that the initial position should be at 0, so I set it to 0. And then also the initial velocity is positive. It's something that's going upwards. You know, the red curve is going up from the initial position, so I know I needed something positive. So I tried 1, that wasn't enough. I see that beyond that, all of the intersections are correct. It's 0 at the same time. So all that really needs to change is the amplitude. And one way to mess with that is to just change the initial velocity. So I just changed it. Maybe 3 wasn't enough until it was 4. So there wasn't a ton of guessing going on in that first one. In the second one, for instance, the initial position should obviously be 3. Well, why is that obvious? I'm claiming it's obvious because here it's at 1, but here's where the red curve should be. So we should start out at 3. So that's not really a guess. That's just knowing that. Okay, that looks pretty good. The amplitudes look like where they should be, but it's not as frequent as it should be. You could experiment with changing the frequency, like I had put up here, that was saying we want to experiment with M. So we could try to, or M and K, either way. If the spring is more rigid, it will try to pull itself back to the equilibrium position faster, or push itself, push or pull. So actually either one of these should work, M or K. With a smaller mass, the spring doesn't have to work as hard to move it. There's not so much momentum change, so it can move faster. Or with a larger spring restoring force, it's more rigid, so it'll move faster. So you can experiment with either one. Maybe I would try like 0.5, lessen the mass, which makes it more frequent. You could try an even smaller mass. Hopefully I don't give it away here, but oh, well, there it is. There's the answer to that one. So you kind of hopefully see what I'm doing here, that there are some things you can say for sure right away, and then it's just a matter of slightly tweaking one or two things to get it to line up. There's a little element of guess and check, but it should be driven by an understanding of what's going on with the system, or hopefully it would be, is the idea. Another question is, how do we find the initial value problem? Once you get the blue curve to overlap the red, that is the initial value problem. So for instance, this now is the initial value problem for 2. It's 1/4 x double prime plus x is equal to 0, and then x of 0 is 3, x prime of 0 is 0. And then similarly, the first one has an initial value problem of, let's get it to line up, of this right here. Again, hopefully that answers your questions. I'm now going to go silent for a second, unless you have more questions. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.